Hello and welcome to the Further Maths video on further mechanics, and this week's topic is power. So looking at the definition of power in the workbook, we need to think of power as being the rate of doing work. Using the formula we already know for work, we know that work done is force times distance. So if we look at the rate of work done, then that's our power, and power is force multiplied by distance over time, and of course distance over time is velocity. So we get this nice equation that power is force multiplied by velocity. This force here, just like with work done, is the driving force or the forwards force, or it's also sometimes called the tractive force. The units for power are watts, sometimes kilowatts, and a kilowatt is 1,000 watts. When you're looking at questions, we say that an engine has a power or an engine develops a power. And it's important to understand that power for a particular engine is constant. So if we have a power, our power equation of power is force multiplied by velocity, if the vehicle starts moving faster, so if this increases, velocity increases, then the forwards force must decrease because the power remains constant. So let's have a look at the first question here. We've got a car of mass 1,200 kilograms moving on a straight horizontal road against a resistive force of 500 newtons. And we're asked to find the power developed by the engine when it's travelling at 15 meters per second and accelerating at 0.25 meters per second. So our first approach here is going to be to draw a large diagram and mark all the forces on. In this question, we don't need the coefficient of friction. We are given the resistive force. So we're going to apply Newton's second law, which is F equals ma. So we've got the forwards force F minus the resistive force of 500 is the mass of 1,200 multiplied by the acceleration, which we are given in the question as 0.25. And rearranging this, we get that the forwards force is 800 newtons. So having found the forwards force, we can now find the power, because power is forwards force multiplied by velocity. So in this example, that's 800 multiplied by 15. And when you work that out, you get 12,000 watts, or you might write 12 kilowatts. Just read the question. Sometimes it asks you to find it in kilowatts. Second part of this question, part B, says find the maximum speed reached by the car if the engine continues to work at this rate. So what's going to happen is that the speed will increase, and that will cause the forwards force to decrease. It will reach maximum power when it's travelling at constant velocity. So that's an important point to remember. Maximum speed happens when the car is travelling at constant velocity, or when acceleration is 0. So acceleration is going to be 0 when the forwards force is equal to the resistive force, which is 500. The power is fixed. So the power is 12,000 watts. That's this new force of 500 multiplied by the velocity. So when we divide that, we get that the velocity is 24 meters per second. And that is the maximum speed that the car can reach. Moving on to the second question. We have a car of mass 1,000 kilograms travelling at a constant speed of 12. Constant speed, as soon as you see that, makes you think that the acceleration is 0. Along a straight road, inclined at 10 degrees to the horizontal. The engine is working at 25 kilowatts, so power is 25,000 watts. Car is subject to a resistive force of R opposing the motion of direction. So the velocity is equal to 12. So the first step to take in this question, draw a large diagram, mark on all the forces. We've got a forwards force, and I'm going to call that T, and we're trying to find the value of R. So first of all, we're going to use the fact that power is forwards force times velocity. So power is, in this example, TV. So 25,000 is equal to T multiplied by 12. And that gives this forwards force here of 2,083.3 newtons. We're now going to apply Newton's second law parallel to the slope. So parallel to the slope, we're going to do some resolving. We've got a force of T up the slope. We've got a force of R down the slope. We've also got this force of 1,000 G. We've got to resolve it. So resolving it, it's going to be sine of 10 when I resolve it down the slope. And that must be equal to 0. There's no net force because speed is constant. Substitute in the values that we found here. So we've got 2,083.3 minus R minus whatever 1,000 G sine 10 is equal to. And when you work that out, you get that R is 381.58, which we would round to 3 significant figures, so 382 newtons. So that's the value of R. Now, part B of the question, the rate of working is now increased. So power changes now. And so we've now got that the power is 30,000 watts. So we want to find out what the new tractive force is. And we want to work out the initial acceleration. It has been travelling at 12. So at the point the power changes, it's still travelling at 12 meters per second. So we're going to say power is T1. We'll have a new tractive force. We call it T1 because we had a different force over here, multiplied by 12. So rearranging that, I get 30,000 divided by 12 is T1. So T1 is equal to 2,500 newtons. The initial acceleration of the car, we're going to resolve along the slope, and we're going to use Newton's second law. So we're going to say T1, which is 2,500, minus the resistive force. So that's going to be 381.58, use the unrounded figure, minus 1,000 G sine of 10. And that's equal to the mass, which is 1,000, multiplied by the acceleration, which is what we're trying to find. And if you rearrange this equation and work out the values, you get that A is 0.417 meters per second squared. So at the moment the power changes, so the forwards force changes, and that generates an acceleration here. So the main points with power questions, remember the equation, power is force times velocity, to look at whether you've got constant speed, and to realise that as the forwards force decreases, the velocity will increase.